So we have a population that's growing according to the model P of t equals 2 times 1.37 to the t plus 32, where P of t is measured in millions and t is measured in days. First thing we're going to do is determine the instantaneous rate at which the population is growing on day 4. So part 1 here, we're going to find P prime of 4. Well, first let's find P prime of t. That involves recognizing what kind of function we have. Well, this piece here is exponential. So a derivative of an exponential always involves itself. Constant up front is part of the derivative. So times 1.37 to the t times the natural log of the base, 1.37. If you want, you can write this out front. That's okay. It's multiplication, so you can write it in any order. Now we also have to take the derivative of 32. 32 is a constant, so its derivative is 0. So right there is our derivative. And now we can find P prime of 4 by plugging 4 in for t. So we'll go ahead and, using a calculator, estimate this value. And we get about 2.218. And this was a population of cells. So that's, the units on that are millions of cells, because that's what our function was measuring, per day, because our input was the number of days. So we're finding out that at day 4, our population is increasing by 2.218 millions of cells per day. So that's our instantaneous rate of change. Now, for the next part, we're actually going to be asked if the population is growing as an increasing rate or a decreasing rate. Well, based on what we know of exponential functions, we see that the base is greater than 1. So this is going to be concave up, so it's increasing at an increasing rate. But let's verify it using derivatives. What we'll do is we'll see what's going on with our second derivative at 4 to test our concavity. Well, first thing we need to do then is find our second derivative, P double prime of t. Remember, that's just the derivative of the derivative. So I'm going to take the derivative of this guy. The 2 and the ln of 1.37 are just constants, so they'll be in my answer, times 1.37 to the t. So notice the derivative has itself in it, and anytime you take the derivative of an exponential, you need to multiply by the natural log of the base. So ln of 1.37. So that actually happens again. So if we wanted to make this a little cleaner, 2 ln of 1.37, and that's getting squared, times 1.37 to the t. And there's our second derivative. Now remember what we wanted to do. We wanted to evaluate it at 4, so we're going to plug 4 in for t here. And using our calculator, we get that this is approximately, all we really care if it's positive or negative to answer the question, but 0.69825. Now the units on this would be millions of cells per day, because we're looking at the rate that the derivative is changing. But because this is greater than 0, we can say that not only is the population of cells increasing, it's increasing at an increasing rate at day 4.